In this video, we're going to be discussing linearization, which is a process of how we can take any nonlinear differential equation or system of differential equations and approximate it as a linear system. And this is useful because we've been spending a good chunk of a semester now talking about various tools for analysis of dynamic systems that work on linear systems. And so if we're able to take a nonlinear system and come up with a linear approximation to that nonlinear system, then we can also use these tools that we've used to um, analyze the damping, analyze the frequency response, design a controller, and depending on how good that approximation is, we'll be able to get in the ballpark of trying to understand these systems. So in this class and in this video, we're going to talk about a specific method of linearizing nonlinear equations, um, which is to take a small approximation of the value and approximate what that function would look like if we zoomed in so far that all the curves become straight lines. Um, so for example, we've got a few nonlinear functions like sum x to the n. So if your dependent variable x, if it's squared or cubed, that would make it nonlinear. We also have maybe an x times y if we have two different dependent variables that are multiplied together, cosine of x and sine of x, and tangent of x. So trigonometric functions of dependent variables make them nonlinear. And one other one that we'll say is e to the x. So if in the case of e, if some constant is raised to the power of our dependent variable, then that makes this thing nonlinear in our dependent variable. And so with any one of these functions, if we say that x is small, um, then we're able to approximate what that value or what this function is um, when when x is small. And our approximations are going to be useful under certain conditions. So for example, with x to the n, um, x, if you raise a small number, if you take a small number and you square it, you get an even smaller number. So what we're going to say is that we can approximate x to the n if the absolute value of the magnitude of x is less than 1, right? And n greater than or equal to 2. Um, in those conditions, x to the n is approximately going to be equal to 0, right? If we're trying to take a linear approximation, then when x is small, the linearization of that is 0. If the absolute value of x is less than 1 and the absolute value of y is less than 1, if you take two small numbers and you multiply them together, you get an even smaller number. So that's also approximately equal to 0. Um, if x is less than 1, the absolute value of x is less than 1, then cosine of x is approximately equal to 1. And if the absolute value of x is less than 1, the sine of x is approximately equal to x. I'll go ahead and draw that picture. If you have the sine of x right here, when x is small, the derivative and the slope of that line is equal to 1. So for small values of x, you're following along with that straight line y equal to x. So the linearized approximation of sine of x is just x. Same for tangent is approximately equal to x if x is less than 1. And e to the x is approximately equal to 1 plus x for x less than 1. And you can see just to show as an example, e to the 0.2 equals 1.22, right? So e to the 0.2 is the nonlinear the nonlinear value of this function. But if we were to take the linearization, we would say e to the 0.2 is approximately equal to 1.2, or 1 plus 0.2, which is 1.2, and that's approximately equal to 1.22. So that gives you a sense of how close this approximation might be. So let's go ahead and do some examples. So sometimes you might see something like the expression x times y plus 5. And you want to take the linearized approximation. You want to make a linearized approximation of this function. And so first what you would do is you would multiply everything through to get individual terms. So you would get xy plus 5x. And now the term xy is a nonlinear term, and it's the two of your dependent variables multiplied together. So xy would approximate to 0, and 5x is already linear, so you would say that the linearized approximation of x times y plus 5 is equal to 5x. We'll go ahead and do a slightly more complicated example. So what if you have something like the sine of x plus 5? So in this case, we know that the linear approximation of sine of x is equal to x, but we don't know x plus 5, so we need to use our trig identities to try and separate this out to get it into the form of some of our approximations that we had up here. So the sine of x plus 5 is going to be equal to the sine of x times the cosine of 5 plus the cosine of x times the sine of 5. Put in some parentheses here. So it's important to remember that the cosine of 5 and the sine of 5, those are just constants, which is fine to have in a linearized equation. But the sine of x is approximately equal to x, and the cosine of x is approximately equal to 1. So the sine of x plus 5 is going to be approximately equal to cosine of 5, which is a constant, times x, so that's a linear term, plus the sine of 5, which is also a constant. We'll go ahead and end that video there.